Welcome, everyone, to this Professional Development Hour presentation brought to you proudly by the Atlanta Metro chapter of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. Before we begin, we'd like to let you know that any opinions presented tonight are solely the opinions of the presenter and not that of the Georgia Society of Professional Engineers, the National Society of Professional Engineers, or any other of its affiliates. We certainly hope you will enjoy tonight's presentation, so sit back and relax, and on with the show.
Okay. Yep. I'll keep it moving. Yeah, I'll keep it moving.
Don't really want to move on.
All right, everybody. Today's presentation is on modern battery technology, and the name of our speaker is John Copeland. John is a co-founder and chief technology officer for Energy Assurance LLC, a fully accredited cell and battery test lab acquired in 2022 by Elements Material Technology. He holds a BSEE, double E degree from Auburn. Go War Eagles. And MSQA from Southern Polytechnic State. He's also trained Six Sigma Black Belt. Please join me welcoming John to our...
All right, guys, I am fighting a little bit of laryngitis here, so we're going to try and keep this going for, hopefully you guys will be able to hear me throughout it. So real quick about our company, we were acquired by Element Materials. Element Materials Technology is a testing, inspection, and certification house. They tend to focus on things where industries where you have very much a criticality about the work that's being done. As you can see, we do quite a bit in the aerospace, automotive, defense, energy, cellular, life sciences. Pretty much a wide variety of about anything you put your hands on, we test it somewhere. Around the company, we've got, it's a global footprint, 260 locations in over 30 countries. So, a little tagline they like for me to talk about is making tomorrow safer than today. So very focused on the safety aspects of things. All right, let's get to the fun stuff. I think we can all agree that the world's changed quite a bit. Everything has either went portable or went networked or is portable and networked. If you're going to have that as your backdrop, power becomes a critical issue. In the past, the idea of having something that required any significant amount of power not connected to the wall really wasn't a viable answer. Batteries have changed quite a bit. Specifically, as I go through this, we're going to focus primarily on lithium-ion batteries because that's what most of the technology is based around these days, but we will talk a little bit about some of the other nascent technologies that are coming out. What's the advantages of them? Well, they're small, they're lightweight, a lot of energy, long life, high power. But that comes with there's kind of a flip side, you know, the other side of the knife edge there. And that is the more that you want to take 10 pounds of stuff and put it in a 5-pound bag, particularly when it's energy, you got a lot of risk there. So that risk has to be managed. The good news is, of course, is that we're all engineers here. We are all doing our jobs to make sure that the technologies keep moving forward. And quite a bit of work going on in our area of the game as well. So specifically, what are we going to talk about today? I'm going to spend a minute just going over terminology so that we're all kind of on the same, you know, when I say one thing, you understand it's exactly what I'm talking about. Spend a little bit of time on battery chemistries, just a quick introduction. I've got two overviews that cover manufacturing, basically how do you make cells and how do you make battery packs. Spend a lot of time talking about safety concerns and touch on the regulatory landscape around that. And then we'll spend some time going over sort of where the automotive industry is right now, because obviously it's going through a lot of changes related to electrification. And then one that, given we have this is a PE group, energy storage systems, things that are typically connected to buildings or the grid. We're going to talk about that as well. And then finally, we'll break out the crystal ball and see what's up on the horizon there. So, starting with terminology, what's a cell? A cell is that basic electrochemical unit that's going to take chemistry and convert it into electricity. I mentioned this, I know that sounds so blatantly obvious, but there's always confusion between cell and battery, so that's why we're discussing it. The formats you see up there are the most common. Button and coin cells, cylindrical, prismatics, which are just rectangular cans, could be metal, could be plastic, and then pouch cells. Think of it as what's the material of the pouch? Aluminum, an aluminum pouch. Nice and lightweight. When you take a bunch of cells and you put them together, what do you get? You get a battery. In some industries, that might be known as a module or a pack. And that's everything from a tiny little single cell that's got one little safety circuit hanging off of it that might be this big, all the way up to a full-size automotive EV pack. Then lastly, you may hear me talk about primary versus secondary. All that is engineer speak for primary means non-rechargeable and secondary is rechargeable. All good? All right. Talk battery chemistries for just a minute, and this is by no means an inclusive list. If you want to get kind of an idea for it, go on to, break out your Wikipedia page on lithium chemistries, and you'll see it's a very extensive table. So this is just a few of them. Everybody's familiar with alkaline cells. Matter of fact, I believe my contact here has some experience working in that area of the game. Pretty much a static technology these days, just hasn't changed much. It's very much a commodity item. Although oddly enough, we've had some personal experience here recently where a very large retail outfit came to us with alkaline concerns, so there are still issues around them. Zinc air, that's what you'll find typically in hearing aid little coin cells. Manganese dioxide, these are like your camera batteries, CR123As. These are relatively benign, although there is metallic lithium inside them, so if you treat them wrong, they will explode. I've seen one go off just like a rifle shot, so they can hurt you. Lithium iron disulfide, if you've been in Walmart lately and seen Energizer E² lithium batteries, this is sort of a common chemistry around alkaline as well. Similar to the way that alkaline is used, this gets used. It gives you extended life, of course, at a premium price. Skip over to the secondary side. Everybody's familiar with lead acid. You got those in your car and your golf cart. Those are obviously two very different things though. The one in your car is designed for very high current for a very short period of time. The one in your golf cart, you're going to charge it all the way up, you're going to run it all the way down, you're going to charge it back up again. Those are commonly known as AGM batteries, or for advanced glass mat. Nickel cadmium, when I was in my formative years, that was the rechargeable chemistry for anything portable. It's pretty much fallen by the wayside. Why? Well, it's got cadmium in it. Nobody wants cadmium in their drinking water or anywhere else. Heavy metals are just hard to deal with. Nickel metal hydride has pretty much overtaken it as the replacement nickel chemistry. They basically behave the same way. Charging is very similar. But truthfully, all your nickel chemistries, for the most part, have been supplanted by lithium ion. Lithium ion came in and got first commercialized back in the mid-'80s, really came to fruition in the '90s, and has just pretty much taken over everything. The four series of alphabet soup there, these are just some of the common lithium ion chemistries that you might run across. This may be something you may see on a specification sheet or something like that. LCO is lithium cobalt oxide. This is the original lithium ion chemistry. Lithium iron phosphate, LFP, is one that A123 made very popular. It's a lower voltage but more stable chemistry, and you find it in a lot of lower end EVs, electric vehicles. NMC and NCA, that's nickel manganese cobalt and nickel cobalt aluminum. You'll also find these in electric vehicles. Actually, you'll find them in about everything now. They are both very high energy chemistries, and as a result, you've got to treat them. Actually, all of these you've got to treat with kid gloves. The design is very critical, or you wind up with safety issues. All right, I told you all that stuff so I could get to things that are a little bit more interesting. This is what's inside a cell. And so the items I have over there on the left, I'm basically starting at one side of the cell and working my way across. So your cathode, T, positive, that's your positive side of the cell. Anode is the negative side. You start off with an aluminum foil current collector, and then you're going to bond active material onto it. And we'll talk more about how that's done here in a moment. That's where all that alphabet soup I had, that's the material that's going to be placed on that aluminum. In the middle next is a separator. This is basically a piece of plastic that ions will go through, but it keeps positive away from negative. What happens if positive touches negative? Bam, exactly. So very important that separator does what it's supposed to do. The anode material for most of the cells we look at is graphite. There are some exceptions to that. And that graphite, same way that the cathode material is bonded to the aluminum current collector, graphite is bonded to the copper side. The three pictures I've got up here, these are a cylindrical cell, pouch cell, and a prismatic cell. And realize it's a bit of an eye chart, but truth is, they're all very similar. Just the difference what the outside case looks like, and then some of the details. I didn't mention it, but what makes it all work is we've got an electrolyte that we're going to pour in there on top of it. Usually this is a liquid electrolyte, although solid state electrolytes are slowly starting to work their way in. Still a ways to go on that one though. So how do you actually make a cell? Start off by making a slurry, actually two slurries, one for the cathode side, one for the anode side. Basically mixing powders together and binders, and I'm not a chemist, so I really can't tell you what all that stuff is. So if you have questions, ask our materials engineer. But anyways, we're gonna mix all that stuff up and make this lovely pile of black goo, and then we're going to coat that onto the electrode. When it goes onto the electrode, it's you know, not totally flat. It's also not really squished down. So the next thing we want to do is we want a nice even height. So we're going to calendar it. We're going to run it through basically some high pressure rollers and get it to a nice even height. That's going to make it behave better. It's also, we want to get a certain amount of stuff inside a cell. So if we don't squish it down enough, we don't fit it in the cell. So it has to be calendared. Calendaring can be a good thing or a bad thing. If you do it too much, what happens? Your active material becomes brittle and flakes off. Not good. Once you've got your electrodes coated and calendared, now you got to cut them. There's two general ways that happens. One is like what you see here, where it's a die cut. And this is used for a method of assembling cells that's known as cut and stack. We're literally going to do anode, separator, cathode, and keep stacking like that. If you are making a cylindrical cell, well, there you want nice long strips, and you're going to roll those up into what we commonly refer to as a jelly roll. The way that is done is that wide electrode sheet is run through a slitter, so it's going to precisely cut those strips to a given width to match the cell size. A critical process control step turns out to be making sure those blades are changed out frequently, because as the blade gets dull, you wind up with burrs along the edge of your electrode. Now all of a sudden, exactly, I saw that guy's face just go, ugh, exactly. Now you got bits of metal floating around in your cell. Ask Sony how that worked out. Not so good. So, critical process control step. From there, the cell is assembled, again, either cut and stack or wound together. A lot of process control and proprietary information around how that's actually done. Suffice it to say, it has to be very, very consistent for the cell to behave like you want it to. And then finally, that is placed inside either the pouch, the can, pouch or the can, and then electrolyte is added, and then we go through what's called a formation charge, which is the first charge that's put on the cell. Voila, you have a functioning cell. Any questions on that?
What is the most critical manufacturing? In the manufacturing variables, which one is the most critical affecting performance?
Well, I would tell you the one that the cell manufacturers cherish the tightest is all about electrodes and coating of electrodes. I visited a couple of factories in Japan years ago that made cells, and they would actually do the coating of the electrodes there at their facility, very tightly controlled, basically a clean room. And then they would put them in sealed containers and ship them over to China for the rest of the cell assembly. So that's the one that was really their secret sauce. I don't know if that answers your question or not. Yes, sir.
I've heard a newer technology being discussed, iron sulfur, as an alternative to hard to get lithium. You have anything on that, or is that more just in talk?
There are a number of iron-based chemistries. I wasn't going to cover them here, mainly because, well, if you like a 4,000-pound battery, it's a great piece of gear. Probably don't want to go portable with it. Wouldn't be my recommendation. But there are a number of variants of that. I believe nickel iron is one of them. There are many, many competing technologies to lithium, and each has its advantages and disadvantages. The catch is that so far, most of them haven't made it to a point of really being commercially viable. There are some that are on the edge of that, but they're not there yet. We're going to talk about a few of those a little later in the presentation. All right, pack assembly. Now that you got some cells, how about we build some packs? The first step actually has to do with the cells themselves. You know, it's an incoming material for an assembly factory. If you're going to put cells in series, it's very critical that they be what's called balanced. Just basically means they have the same capacity. If you think about it, if you have a number of cells in series and you go to charge them and one of them is lower than all the others, what happens to that cell? Well, it gets overcharged actually. And yeah, that's actually what happens is the cell, you're causing it to premature age. And so it will start to become less of a cell and its impedance will go up. Similarly, when you go to discharge it, if it's too low a capacity, you over discharge it. Again, aging the cell and potentially leading to safety issues on both ends of that. So there is quite a bit of incoming work there that's done. Next is you've got to start joining the cells together. So those next two steps there are where you are going to take your cells and typically join them together with tab material or a tab-like plate. The connections can be anything from resistance welding is very common. For certain applications, laser welding is used for added precision. Ultrasonic welding is used. Wire bonding is used. Please don't take a soldering iron and try to solder them together. That's always a bad idea. But yeah, it doesn't work well, and you can kind of wind up with a cell sticking out the front of your head. Anyways, that's the way that the cell is put together, or excuse me, the module is put together. From there, the module will go through some basic testing. And I didn't mention it, there's actually more that's attached to it at that point besides cells. You're also going to have some form of either safety circuit or battery management system. So this is kind of the brains of the battery. The old days of batteries just being a couple of cells are kind of gone here. If you have that, you have a dangerous battery. Anyways, testing will go on at the module level. And this is sort of, keep in mind that this is really talking things like EV packs, where you have cells to modules to battery packs. So battery pack assembly is next, followed by more connections, more testing, and then some final assembly if they get through all the required tests. Finally, some get the charge state set correctly, final out the door test, and away it goes into a vehicle. I know I'm grossly oversimplifying that, so if you have questions, let me know and I will gladly respond. So what about safety? Everybody's seen flaming battery videos on YouTube, right? Flaming Teslas, flaming, yes. Which is more dangerous, an electric vehicle?
Houses from flaming batteries.
Sometimes, yes. Which do you think is more likely to catch fire, an internal combustion engine or an electric vehicle-based car?
Internal combustion is right there in the name.
Sometimes becomes external combustion and you have a barbecue. The rate of internal combustion engine fires to electric vehicle fires is right about 98 to 1. You wouldn't know that though if you watch the news. You would swear Teslas kick off about every 10 seconds, but that's not the way it works.
And you'd have to buy a new battery for your Prius every 3 years.
I'll tell you a trick about that here in just a minute. It's just a question of what's newsworthy and what's not. I mean, we all live in Atlanta. We see fires on the side of the road probably pretty frequently if you do the commute in and out of the city. I was told a story here once about a news report of actually what you just described there, Roger, where a house had burned down and they showed the picture of the Tesla out in front that had burned. Well, they got the story wrong. In reality, the house caught fire. The fire jumped to the car, which then caught fire. The problem with lithium batteries in general, though, is the fire is very hard to put out. So let me take a step back here. The deal with lithium batteries is they're subject to a condition known as thermal runaway. This is how you get into trouble, and it's basically a case where you're producing heat faster than you can get rid of it. The battery itself will get into a bad situation and start self-heating. That heat now causes the reaction to go faster, which in turn produces more heat, and you get into this vicious circle. Once you're in that, it's kind of hard to get out of because it happens basically exponentially. If in your larger, more sophisticated packs like you find in an electric vehicle, you have temperature sensors all over it, and they can potentially do things to mitigate that before it becomes a problem. There's actually a lot of really smart people now working on ways to look at data that comes off the pack and figure out smart ways to tell when it's headed in that direction so that they can advise the driver, shut down the car, do something, safely get it before it goes into runaway. I mentioned that the fires themselves are hard to put out. Everybody seen a fire triangle before? I know my Navy guy here has seen a fire triangle more than once, so yes. 3 things you need for a fire: fuel, oxygen, and heat. Take away any one of those 3 and you don't have a fire anymore. Well, in the case of a lithium-ion battery, starting with the fuel, the electrolyte's flammable. It burns and burns nicely. Second is that once you get things burning, the cathode actually will release oxygen. Not a lot. It's not like an O2 tank going off, but think of it, the fire department puts out the fire, it's still hot, it's still smoldering, and then all of a sudden, an hour later, comes back up again. Builds up a little bit of oxygen, enough to get a fire going. So if you've got some source of heat, being an internal to the cells themselves or an external source like a house fire, you can definitely get a really nice fire going there.
How do fire departments put out fire?
Water.
Just water?
Water is the preferred firefighting measure. And the reason is because you're trying to get the heat away. There are some fire departments that have to deal with car fires. They literally have like one of the large dumpsters with a crane. They will bring that out to the site where the car is that's on fire, fill it full of water on site, take the crane, set it in there and leave it for a week just to get all the heat out. So yeah, water's still the best answer.
Do you have any statistics on internal combustion vehicle fires? How many of those fires are actually initiated by an electrical problem though?
I do not actually.
Repeat his question.
Yeah, sorry. His question was about if I had any statistics related to the source of internal combustion engine fires, was it electrical or something else? My guess is probably a substantial number would be electrical, but I don't know personally.
I'd guess a water because people are stupid and don't change or check their oil.
Yeah, might have something to do with it.
Everybody has seen the high school demonstration of elemental lithium dropped in water and it buzzes all around the container.
Yes.
But still water is the preferred because it's not elemental lithium?
Exactly. So in the case of lithium primary batteries, and we'll talk about rechargeable lithium metal here in a little bit later, the ones that have elemental or metallic lithium inside them, those you do not fight with water for the reason you just noted. Lithium, sodium, all those, you mix water, you get hydrogen heat and a nice explosion. Lithium ion is different. There, everything's ionic. You don't have metallic lithium, assuming that the cell has not started misbehaving and you've had lithium played out on the inside. So yes, for lithium ion, still water. I stole this from a guy at UL. This is one of his public papers. But it's a pretty good little description here. And you notice what's right in the middle there? Internal heating. That's where everything kind of happens there. Usually it's either you've got something causing a short inside the cell that causes a current flow and thus generates ohmic heat. I'm not going to go around all the different pieces of this, but essentially if you get in that loop of a short, generates heat, causes a separator to become compromised, and then eventually plus and minus come together, you get a really nice explosion. You guys ever want to see what one of those looks like? So this was a prototype rechargeable lithium metal cell that we tested back in 2018. It was only about that big, right? You probably can't see it too well. It's actually sitting right at where the end of the fire is, facing that way. What we're doing in this is a nail penetration test. We're driving a nail right through the center of it to see what happens, because we're sick people and we just really like doing that kind of stuff. We did. Well, yeah, absolutely. You guys pay me to do that stuff, so I'm glad to do it. What's interesting is that this was a still shot out of a video. If you notice the little pieces of white flying all around, that's burning lithium. The next frame of this video was this color right here. It went totally white. Yeah. We're looking through a piece of fairly thick safety glass there in a hood. It cracked the glass. Serious stuff. You know, when we tell people not to disassemble lithium batteries, there's a reason. This stuff can hurt you, seriously hurt you.
Question?
Yes, sir.
I've seen on the airlines they now have a blue bag that you first see. What's special about that blue bag?
I'm not sure the answer to that. There are some products out there that have, is the word intumescent? Is that the right word?
Note 7 was famous.
We'll get to that one in a second. To your question, in some of those bags, they have a material that acts as a Class D agent. It actually acts as a fire suppression agent. And so you're basically containing the fire within the bag. It's still going to smoke like crazy, and you know, bits of fire may shoot out the sides, but for the most part, you're containing it. And that's only good for, you know, relatively small devices. Yeah, anything that's big, no, it'll pretty much blow it apart. I have seen some that are designed for larger batteries, and some work and some don't, and I'll just leave it at that. The Galaxy Note 7 was interesting because it was two different defects. There's a very good report that was published publicly. It was done jointly by UL, Exponent, and I forget who the third one. Yeah, UL took most of the credit. That's usually how it works. But yeah, two different defects inside it. One had to do with the corners of the cell. The phone was such that the corners were rounded inside. Inside the cell, things weren't rounded. So if you try to do that, now you're collapsing layers together. That was one problem. They had multiple vendors. A second vendor had a totally separate problem that had to do with the welding along the center. Yeah, so multiple cells, types, different problems. Yes, sir?
Yeah, is there lithium iron phosphate? Is there any difference? Is there any safety difference between that and lithium iron phosphate?
Very much so. So lithium iron phosphate is a lower voltage, more stable chemistry. There's always that trade-off between stability and energy density, and that's literally what it is. The iron phosphate it's relatively inexpensive. You have to use more of them though because your voltage is lower, your capacity is also lower, but it's a safer alternative.
So it won't do that?
I didn't say that. It'll definitely do that. I haven't seen too many of those that won't do something, maybe not quite that dramatic, but no, it can go into thermal runaway, definitely.
So would you treat
Your handling of an LFP battery any different than like an NMC, or just treat them all the same across the board?
probably treat them all the same is going to be the best answer. When we're testing them, we're going to treat them differently because we're intentionally abuse testing, so we know that an NCA battery is a lot more volatile than an LFP battery. A nickel cobalt aluminum versus a lithium iron phosphate. But for consumer handling of it, and even anything you guys would be doing, you should treat them the same. The firefighting is the same. The actions in case of emergency are the same. It's just one's a little more volatile than the other.
We're being encouraged never to not routinely fully charge the Tesla's normal lithium-ion batteries, but I think the LFP cells you can charge to 100% all you want with no detrimental effect.
I wouldn't say that. Okay. So, as a general rule, the most stressful time for a battery is when you try to fully charge it, and that's normal. You know, your cell phone's fully charged. Computer manufacturers have gotten smarter, though. They've started noticing like how do you use your computer. You're like most of us. I mean, most of the time it's sitting on our desk plugged in. So in that case, most of them will not actually take it back up to fully charged. They'll go up to like 80 or 90% so that you relieve some of that stress. There's an interesting anecdote I tell people, and I don't take this as 100%, you know, every single one does it this way. But a long time ago I was told that the auto manufacturers, whenever you buy a new electric vehicle, right, they will give you, there's a 10-year warranty associated with that. I mean, that's what the automotive industry always does. Designed for 15, hope you'll get 10, right? Well, batteries were no exception to that. The problem is not all the batteries really are designed to last for 10 years. They're more in the 3 to 5 year category in some cases. Some longer, but so what they did was they got smart. I can fully charge it up to here. I can fully discharge it down to here, right? When the car is new, do you think I do that? I'm going to start here. So to the consumer, when they first charge up that battery and they see what its mileage is, they get a certain comfort around that. As the car ages, we'll push this limit out a little bit, push this one out a little bit. And so over time, initially they never got the full initial capacity off that battery. It was there, they just didn't have access to it. But it made it such that as the battery was aging, they felt better about it, basically. And it didn't change. They didn't get a whole bunch of anxiety. Oh my gosh, I was getting 450 miles, now I'm only getting 400. Yeah, but you're still getting 400. It's not a logical thing, it's an emotional thing, so.
You mentioned this was a nail penetration test?
It was.
Is there a body of ASTM test batteries?
Not that I'm aware of. Most of the testing is for batteries is things like, so a lot of UL standards, IEC standards, international. There's what is it? Used to be called Freedom Car that the automotive industry uses. I forget the name of it now. There's some unique standards by industry, like for aerospace, they use RTCA standards. So. But actually not much in the way of ASTM. ASTM, we always saw as more just the material side of it, not the end-use application. All right. So now that you know what one looks like when it's going to cook off on you, what can you do about it? Well, it all starts with design, right? What is it you're going to spec as an engineer to put inside that pack? So coming up with the right specifications and enough margin around it obviously is the right thing to do. Because you're always, what engineers do, we're always making trade-offs. It's three-legged stool. I mean, if I got more over here, I got to take less over here. So it's nothing unique there. Once you've figured out what those specifications ought to be, this is the critical step. Make sure you get a high-quality cell. As an engineer, if I tell somebody I need a 2 amp hour lithium-ion cell that's 4.2 volts, there's a whole bunch of options that fit that. Some of them are really nice, made by reputable manufacturers, and some Chinese guy did in his garage out on the farm. And I'm not kidding about that, I'm quite serious. I mean, if you look at what's happened now, actually, I'm going to hold off on that. We'll talk that in a minute. Cell failure rates actually aren't bad though. If you get a good quality cell, it's somewhere around 1 in 5 million. Of course, on balance, how many cells got manufactured per year? How many do you think? I'll give you a hint, it starts with a B. So the last data I have was, I think it was 2019. And it was somewhere between 9 and 11 billion cells got manufactured globally. That's everything from small coin cells up to full EV size cells. So quite a few. That's for high quality cells though, right? Is everything a high quality anything? No. There's plenty of junk out there. Counterfeiting, big part of what Emily does. Her group is looking at people will send us cells and ask, are these legitimate? It's getting harder to tell. Counterfeiting guys are getting better. Actually better quality too for what it's worth, but I mean, it's still not great, but it's getting harder to detect. I mean, when I used to work for Motorola, I did a lot with our brand protection folks. And we could tell the counterfeit products a lot of times just by what was on the label. I still remember this one that said Motorola on it. Yeah, they got it spelled wrong. They're getting better. I mean, the artwork's getting better. You know, it looks, from the outside, it looks the same. You go and do a CT scan of the header assembly and it's totally different in there, and you check the capacity and it's terrible, but it looks right. And so to somebody that, you know, if they don't know what they're doing, they will overlook it. This was that last piece that says supply chain. That's the point I was going to come back to. If you look around the industry right now, all the good quality cells, or the vast majority of them, get sucked up by the automotive industry. They just have such an incredible need for cells and incredible buying power. So they get almost everything, and then everybody else is kind of on allocation. So what that means is, for the poor guy that's making consumer products, that third or fourth tier supplier that he wouldn't have talked to 10 years ago is now his best supplier. So what does that mean? Lower performance and greater risk. Just the world we live in, probably not going to get better here in the short term. When you move up to the pack level, there's some things you have to do to mitigate risk as well. Those 4 things you see up there are the things you want to prevent. Overvoltage is very critical. Most cells are a 4.2 volt cell. Newer ones maybe 4.45 volts. For those 4.2 volt cells, if you get them up around 4.5, they'll cook off. Crappier cells, even lower. Overcurrent during charge and discharge, obviously you don't want to go short in cells. You also don't want to charge them too fast either. They don't really like that. And then undervoltage, primarily a performance concern, but if in gross cases, you can actually get metal plating out on the inside of the cell. So you see this thing sitting right here on the end of this pack? That's how we're going to prevent some of these things. When you do prevention, you can actually start with some passive preventions. It's inexpensive and it works great. But these are usually used as secondary protections. So these are things like fuses, current fuses, thermal fuses, combination fuses. We also see a lot of what's called a PTC. It's also a brand name, you might have heard it called a poly switch. It's basically a resistance that as you run too much current through it, it will warm up. Actually, if you just make it hot, it will do the same thing, but basically as it gets warmer, its impedance goes up. So it tracks impedance with temperature. Most of the work though is done by safety circuit, sort of like the one you see there on the side of this one. And this will have all those protections that you saw listed up there at the top. You can actually go a step past that and have what's called a full battery management system. You find this in your higher tier products like medical devices, automotive, aerospace, and the like. And this takes those same safety functions. It may have redundant safety as well. So you may have a second tier of safety or even a third tier. You also may add communications like SM bus or CAN bus. And basically, like in your computer here, your battery and your computer do talk to each other. They live in the same neighborhood, they speak on occasion. Because if something's going wrong in that battery pack, the host device needs to know about it so that it can act as well as the battery pack. And needless to say, you can do all of those things in combination as well for even, more of a defense in depth type scenario. What else can you do? Well, we said heat was a problem, so anybody in here do ice pack simulations? Any thermodynamics folks? Good. Ugh. Stuff's just wrong, yeah. But anyways, on a serious note, if you design your battery pack, or any device for that matter, but battery pack here, to get rid of that excess heat, either passively or actively, that makes the system quite a bit safer. Also, if you do get into a situation where perhaps the cell has went into thermal runaway, you want to make sure it doesn't spread to the next cell. That's a big deal. Because if it propagates, little problems become big problems really fast. Suppose I'm a contractor and I've got my drill, and I've got quite a few lithium-ion batteries sitting in the bottom of that, and I drop it. Kind of important it not explode, right? Do you know that we do testing for the power tool industry? Do you believe that we do testing at 30 feet on a battery? 30 feet to concrete. And guess what? They all pass. I think 2 of them didn't pass, sorry. Most of them pass, yeah, because they designed for it. If you are obviously building electric vehicles, well, you've got a certain vibration load that car goes through, a certain G load. What happens when you hit a pothole, shock load? So all those mechanical considerations come into play too. Suppose you're designing something that is going to be mounted outside near the beach. I grew up in Panama City, so I tell you all about saltwater damage. It's lovely. If you live up north, snow, same reason, salt on the roads. Corrosion may be a big concern. If all this protection you put in place around your battery is defeated by a little bit of salt getting into your pack and causing your circuit to go haywire, well, what was the point? Fire enclosures, I'll note that as well. Some of the batteries we test do have a fire enclosure. That's one of UL's lovely strong requirements there. Other times it's handled by whatever the host device is that they're fitting inside. Are you going to stop a thermal runaway with it? No, but you might maybe keep it a little smaller. So how is some of this stuff enforced? There is a regulatory landscape around batteries. I'm sure that would not surprise anybody. Politicians, I'm sure, would love to have a whole lot more as well. These are just some common standards up there that you'd ask me about ASTM standards. These are some of the more common ones we see for smaller packs. What does that buy you? Well, if you go through and your product is put through a regulatory requirement, in addition to it being tested to a safety standard that's applicable for that kind of product, more than likely there's also factory inspections involved. How frequent these are varies by the regulatory body. I've seen them once a year up to as many as 4 times a year. Just depends on what they consider the risk and probably what the risk was and what your findings were. The other piece obviously is you get some sort of mark on your product, which is visually obvious and is something that you can go on the web and look up and see that it's viable. When Emily and her group are doing evaluations of products, they tend to start on the outside, work their way in. One of the first things they check is the regulatory marks. Is this real or is it just lovely artwork? Counterfeiters love to make artwork. So if anybody's curious, the 3 on the left, we're a third-party lab for them. The 2 on the right are my competitors, but I figured I'd give them a shot anyways because I know how crappy they are. So, what can you do past regulatory stuff? Well, more than likely you're going to be doing performance testing anyways, right? It's not just, yeah, your product has to be safe, but oh yeah, it'd be kind of nice if it worked too. So when you're doing performance testing, what we find is that a lot of times that performance testing will sometimes eke out little safety issues as well. So definitely good things to do there. Some people will do application-specific safety testing, like I was mentioning a minute ago with corrosion and drop, mechanical, those type things. That may not be a part of the regulatory requirement, but people will do that in addition to it. Emily loves to tear down cells. Tell you what, you guys all back me on this. You tear something apart, you can learn all kind of stuff. You know, what are the overt defects? What are the latent defects? Go take something and drop it 30 times, then open it up, see where the witness marks are. I mean, it's pretty good stuff. The hope there is that you're finding all these additional sources of failure, but that doesn't necessarily tell you about how severe those failures might be. In our world, thermal runaway is the worst case. We do intentional thermal runaway testing up our way. Yes, we make batteries explode. Why? So we can see what they're going to do. What are they going to do when they're connected to the end product? What would they do if they were in a shipping box and UPS was transporting them from point A to point B? What's going to happen? You know, if you guys all see the pictures up here, shrapnel? So that picture really doesn't do that justice. That was a D-cell, you know, flashlight battery size of a primary non-rechargeable chemistry called lithium thionyl chloride. This is not one you go down to Walmart and buy. It's used for things where you need, let's say you needed to keep a voltage on something for 20 years. It's great for that. Or maybe you need your battery to operate at minus 60 degrees Celsius, or maybe up as high as, depending on how the chemistry's tweaked, I've seen them go as high as 100 degrees Celsius. This thing still works. Pretty impressive. What's the trade-off? It's a bomb. Yeah, this was one that exploded in our lab. We did not mean for it to explode in our lab. With much embarrassment, I'm the reason it exploded because I missed something when I was evaluating a project. And it was inside a box, in a metal containment box, so it was contained. But it literally took that box, which, think like a contractor's box. You know, a guy's got it on the back of his truck, 4 or 5 feet long, about that tall. It picked it up off the ground and flipped it over. That's because 3 of those cells went off at the same time. Yeah, a lot of juice in there. It contained all the shrapnel, that's the good news, but that is actually heavy gauge metal. Finally, in addition, there's always the back end. You know, when something goes wrong out in the field, never fun to deal with. If you guys have ever been through a recall before, you know it sucks. I've done one of those, I don't ever want to do another one. But you learn a lot from it too. Sadly, some lessons that you wish you'd learned much sooner. Any questions on that? All right. Thought we would jump into a couple of, just kind of talk about sort of where the market is and sort of where the world is right now. We'll start with automotive here. Anybody thinks that electric vehicles are new? They ain't. I've actually seen that. I went to there's a very large battery show that's right up outside of Detroit in the spring. And I remember walking into it and I saw that thing sitting in there. It still runs. What was really neat though was at that same show, I saw an electric monster truck. Ugh. Yeah, cool stuff. The big deal though was when, you know, some of the earliest cars were actually electric, but the problem was the battery technology just wasn't that great. So it was truly a very short range proposition. As soon as the internal combustion came around and you had that whole gas station infrastructure that got put in place, this just kind of became a relic of the past. Now, did it stay a relic of the past forever? No. What happened? Skip forward to like the 60s and 70s. I know I see some gray hair in there, so everybody remember a little OPEC oil crisis? Yeah, well that inspired some really enterprising designers to really just put their skills you know, out there out for everybody to see and come up with some lovely designs. It was a response to fuel shortages. People got real concerned about that because we were used to, you know, gas that was 30 cents a gallon. All of a sudden that changed overnight. The world also started worrying about pollution. You know, a lot of stuff comes out the tailpipe of, excuse me, an internal combustion engine that ain't good. So health concerns and environmental concerns. Still in those days, what was the chemistry? Well, it was primarily lead acid and nickel cadmium. Had started to work its way in, but it really wasn't there. So yeah, it was a little better than it was in 1901, but not by much. They were intended mainly as little city cars, so and they were okay for that. Then we had kind of a watershed moment. The Prius came out, slowly I might add. really good mileage. Not exactly a car you're going to go win a lot of races with. It was a hybrid, right? So you've got a small gasoline engine that drives a generator that runs electric motors. Not too bad. Just wasn't really that sexy. So, but it did inspire some neat things. One, it sort of taught the country that, you know what, this could actually work. Because in the past, nobody thought it would. It also inspired some other technologies here. If you guys have heard of start-stop technology, it's where you take a regular gasoline car, you put a small battery and a small electric motor, because where do internal combustion engines suck? Right when you go to take off. That's where you burn all your gas while you're working up through the gears. Electric motors are constant torque. They love that stuff. So you run your start and stop off of, or run your acceleration off the electric and then cruise with your gasoline. All of a sudden your mileage that was, 25, 30 miles per gallon goes up to 50 or higher. On the back end of that, you do regenerative braking and you recharge. The other thing was that people noticed that, well, I don't drive very long distances. It would be really nice if at the end of the night, how about I just plug my car into my house and charge up that little battery in there? So after that came the plug-in hybrid. All good stuff, not sexy. Let's go sexy there. Now all of a sudden you go fully electric. Battery technology is caught up. You got lithium batteries that are nice, really powerful. You had a whole lot of, it wasn't just a battery, of course. It was the whole manufacturing process. The electric motors became hyper efficient, and a lot of work still going on there. But now, you got a car that tops out 200 miles an hour. If you guys ridden in a Tesla before?
I don't know in the Taycan.
Oh, what?
It's like muscle car.
Oh yeah. I mean, it'll throw you back in the seat, just pure power. And all that with a 300-mile range. Now, it's perfect? No, they're still a little on the pricey side, but price is working its way down. Anybody think the internal combustion engine is dead?
No, I love it.
It's not going anywhere, not anytime soon. There are, my wife just bought a new car here recently that's a Kia K5, and that's a turbocharged 4-cylinder full-size vehicle that gets 35 miles per gallon. Oh, not bad. And it was an what's that?
40.
Hybrids will do better, don't get me wrong. But I mean, it's not going anywhere. It's going to be around for a while, and they're going to continue to innovate it as well. As I've noted, hybrid is still certainly an option out there. It's becoming least favored over the battery electric vehicles, but I think it still has its place. Why? Because we don't have all the infrastructure we need to charge your batteries all the time. Hydrogen, right out there on the horizon. I remember in the 1970s, people were running their cars off hydrogen tanks. You had water that would come out the tailpipe. Nice and clean, kind of. I found a catch to that recently. You can run a hydrogen engine and literally have drinkable water come out the tailpipe. That works. However, to run a hydrogen engine, a hydrogen combustion engine, at a level that's really good for what we expect as owners of automobiles, you got to run it harder and you actually get nitrous oxides coming out the tailpipe. So not a perfect solution, but a step in the right direction.
Does hydrogen have enough energy density?
Kind of. Relative to what? I mean, it will. You can certainly run vehicles on it.
Gasoline?
Not as much. Certainly not as much, and you have to compress it, so it's very cold. You got high pressure tanks in your vehicle, but it will work. And I think right now it's Toyota or Nissan, I forget which, that has a hydrogen vehicle they're running out in California. Probably a fleet of them. Yeah, exactly. It's out there, so it's being tested, and part of that is to understand the infrastructure that you need behind it. So, yeah.
Speak to recycling or what you do with the product when it's spent.
It's coming. Yep, we'll get to that in a second. There are some reasons that electrification can't get there as quickly as some people would like it to. If you look at where the raw materials are for batteries, China, yes. China, Africa, places other than the U.S. A lot of places that people really don't care for us that much. Now, like cobalt, which you find in like the Congo, I think that's where the largest deposits are. There's a very much an effort to engineer cobalt out of batteries. It's been reducing over time. I've actually seen some now that they've done a cobalt-free lithium battery. So there are ways around it through engineering. Here in the U.S., the federal government is throwing money at the problem big time. So you had, not too far from us here up in North Carolina, you have lithium mines. They've been closed for the longest time because they weren't efficient to operate relative to where you could get your lithium from globally. They're rethinking that. Same thing out in Nevada. You have lithium flats out there, basically huge piles of lithium brine that they leach the lithium out. So those are all, that's all things that are happening. It's not just the raw materials though, it's processing. A lot of the processing right now is where you think it is, China. So building that infrastructure here in the U.S. is going to take some time. On the manufacturing side, remember, we can't build cells fast enough globally. We certainly can't do it here in the U.S. And the U.S. and Europe are very far behind relative to China right now. China has something on the order of 100 gigafactories over there cranking out cells. I think here between us and Europe, we're somewhere around 30 now. So not even close. The unit cost of the vehicles is still high. It's still, you know, still a rich person's car right now, just because of the technology. And it always takes time to work down that, you know, down to the economy level, and it will happen. There are quite a few of them out there that are smaller vehicles, you know, more no frills. I've seen some that are single person vehicles. These will all have their place. And then as we mentioned before, infrastructure is really not there.
There's one that's not on your list, and that's the political decisions about who can tax it.
Political decisions about?
Who can tax the power and who can supply it. That's
always.
legislature now.
Yeah. Yeah, there's always a whole political dimension to all of this. I'm not smart enough to understand it all, so I just kind of accept that and move on. And it changes quite a bit. Yes, sir. All right. Almost there. Haven't got much. I got about 7 or 8 slides left, I think. So I'll speed it along. Somebody asked me specifically about reuse and recycling. Of course, those things should be done in that order. Reuse as much as you can. In the case of electric vehicle batteries, what state of health, what percentage depletion do you think an EV battery is that's considered end of life?
80.
Exactly, 80%. So it's 20% depleted. It's still got 80% of its original capacity in it, but for a motive application, that's not good enough. So what do you do with that? Well, a lot of people got the idea of why don't we take all these EV batteries, connect them all together, put them in a big shipping container and make an energy storage system out of it. Reuse. What do you do when that can't be used anymore? Now you recycle it. Where do you recycle it? Right here. And Georgia is one of the ones leading that, actually. Someone was asking me the question as we were coming through the line there about, what about recycling? A lot of technology being applied there, a lot of new breakthroughs. And the big thing is getting it here in the U.S. because if you've got all these critical materials here in the U.S., the last thing you want to do is ship them back outside the U.S. again. So, yes, sir.
I got a recycling question.
Yeah.
On LFP.
Yes.
There's a lot of projects are going.
So, I'm in the industry too, on the battery storage side. So, BESS.
Right here in Tucker?
I work on my house.
Oh, okay. Okay.
Projects are not in Georgia.
Got it.
They're everywhere else but Georgia. Right? So, recycling LFP, right, versus the previous technology at MC. So LFP is more of a salt type material. So can you elaborate a little bit on the recycling? And I know Tesla's doing it. There's a couple of other people that may be doing it, but that would be a concern about 5, 10 years from now, 10, 15 years.
It will be.
What to do with all these batteries that are being installed. So.
I don't have the answer for you. I know there are a lot of people working on that, but I don't know it myself. Yeah, sorry. I test batteries, I don't recycle them. I simply send them off to a recycler to have them recycled.
That the lithium-ion batteries are almost 100% recyclable.
Well, he's asking about one specific chemistry that has a different, sort of a different...
influence its acceptance.
It's pretty widely accepted, but you're right. You know, you've got a certain amount of time before the glut of that particular chemistry sort of makes its way to the recycling pile, so there's time to figure it out. And people are economically incentivized to do that as well. Definitely. Good question, though. Yes, sir.
So continuing to the in Georgia, because we said that in Georgia we did recycling. So what we're doing, we're putting back in the ground what we're doing.
What do you mean?
So you stated that we're recycling here in Georgia.
There is.
Where? What are we doing with the batteries?
I know there's a place down in South Georgia that I don't know exactly where it is. Ascend Elements is one of them that's here. There are multiple places, but I know they have one facility that's down somewhere in South Georgia. The way this stuff is done, from what I understand it, it's basically a big furnace. And so they're basically breaking down all the materials, and they're pulling off, you know, cobalt and nickel and whatever else.
So back to my LFE, is there any salvageable materials that would be beneficial? Because getting it, cost to get it from the field into a recycling facility would probably be, it's not going to be cheap.
That's the value proposition. I mean, if you're the guy that can figure out how to recycle things economically, I mean, that's kind of a requirement to be in business. So I'm sure the answer will eventually be yes. But again, I couldn't really tell you what it is. All right, this one's a little quicker. Talk a little bit about energy storage systems. This is just basically kind of lay out what they are. These are big batteries for, well, everything from small batteries to big batteries used in different ways. Start off on the portable side. Everybody's seen the little tiny single cell power banks. Yes, be careful with those. I've seen some that were designed so poorly that they would melt the USB plug.
Yeah.
Yes, no kidding. Yeah, most of them are not that way, though. I mean, when you get up particularly into the larger ones, like you see the one there with the solar panel, that's designed for people that do a lot of hiking. They can throw this on the back of their pack and walk through the woods and charge it up over time there. The two below it are interesting, though, and this is, these have started really coming out on the scene the past couple of years. And what you're seeing is they're effectively a generator replacement. People will, like, say they go camping in the woods, they bring their fold-out solar panels, they connect them up to one of these things and charge it up in the daytime. They got power for their needs at night. Some RVs have that now instead of, you know, some generator that you pull out and run off gasoline or diesel. This becomes a very viable alternative to it. On the residential side, I don't own stock in Tesla, by the way. That just happened to be those pictures I grabbed here. Those are the Tesla walls. You can run those in a purely, you know, off the grid setup. A lot of people still grid time as well, sell back their excess power to utility, and then keep enough on hand so that they've got a way to sort of overcome peak hours if they're on that type of rate plan, and then obviously emergency use if the power goes out. When you step up to commercial, it's the same thing, just a lot bigger. Now you're moving into three-phase power, a lot more controls and monitoring and the like. This is used quite a bit for demand planning because obviously in a commercial situation, you've got peak hours that you're dealing with, peak rates. So if you can charge things up when it's cheap and then reuse it locally when it's not so cheap, that's quite a cost savings.
But everybody's going to be using power at night and never going to be cheap again.
Well, I heard an interesting thing about power plants, and that is that, you know, power plants are always designed for the peak, right? And batteries, grid level energy storage systems provide an alternative to that. So now, it used to be that you would run your, you know, at some base load in the evening and at night, and then in the daytime, when everybody needed air conditioning and all your industrial capacity was running, it would ramp up higher, and then that would taper back off again. If you take a really big battery, and by really big, I mean like, think of a large piece of property with containers as far as the eye can see, and you connect those up to your power plant. You run your power plant level load 80–90%, you know, and you charge up your batteries with the excess power in the evenings. Now when you hit midday and everybody has peak needs, you crank on your batteries in addition to your base load that's being provided from your primary source.
That's essentially peak shaving, which is,
it is
done now with hydroelectric and gas turbines and so forth that can be brought online.
Exactly. You stole my thunder a little bit here.
I'm sorry.
And also,
That's okay.
A lot of people express concern.
How are we going to power all these electric vehicles? And that midnight charging is going to be the key to much of it.
I used to drive a Nissan Leaf. I had one for 3 years. Best car I ever had, quite honestly.
Adopter.
Yeah, enjoyed it. It was great. Great performance. But I was on Georgia Power's EV plan.
2 cents.
Less than that. Less than a penny, actually. Yeah, and that was from 11 at night till 7 in the morning. And it was a little, you know, a nickel during sort of your normal hours, and then your peak hours were killer in the summertime. Exactly, yeah.
What that enables them to do is to run the big steam power plants at a higher level.
Yeah.
And then it reduced the amount of peak shaving that they had to use, which is higher cost per kilowatt.
Exactly. So if you can run your power plant more efficiently, supplement it with a whole bunch of batteries sitting over there, it's also less of a regulatory burden. You know, if you have to build a power plant, that's a regulatory nightmare, especially if it's, you know, something like, I don't know, nuclear. But even, you know, just turbine plants, it's still a lot of time, a lot of investment, as opposed to a bunch of trucks show up with a bunch of containers and electricians come up and connect them all together. So much easier. There are some other stuff out there. Capacitors are actually out there. Lithium-ion capacitors, which is sort of a hybrid solution between a capacitor and a lithium-ion battery. Great for high power needs. Gravity. You're talking about filling up reservoirs, upper reservoir, lower reservoir. Use your clean energy, your nice green energy, to pump the water up the hill. Then when you need it, flows back down and runs your generators. Flywheels are still out there as an option. Thermal batteries, oddly enough, they've actually started sneaking into the scene in the academic space now. Talking about even 50% efficiency. It's pretty unheard of in the past. I know I'm getting a little close on time here, so. What's coming out on the horizon? Silicon is one of the more promising technologies out there. And this is where you're taking silicon and kind of sprinkling it into lithium-ion batteries. It gives them a lot of advantage. It would be nice to be able to use silicon by itself, but when you charge and discharge batteries, you'll actually hear people refer to it as breathing. Battery breathes as it's charged and discharged. Well, silicon is a bit on the fragile side, and over time will crack. So when they've tried to do high concentrations of silicon, they would get maybe 100 cycles and it would physically crack. They're working on that. There's people doing some neat things like doing three-dimensional structures to try and overcome that and have increased flexibility. We'll see how well that works out. Emily, she can tell you all about this one offline, but we've tested quite a few of these silicon-based batteries, and when they burn, boy, they burn hot, to the point that they actually melt tab material. So funny how the people that are selling that kind of neglected to mention that to us. Solid-state batteries. Solid state just means we're taking that liquid electrolyte that's flammable, we're going to replace it with something that's solid, hopefully less flammable. They've been talking about this for quite a while, years. Every time we go to a battery conference, there's, you know, a huge number of folks extolling the virtues of solid state and how their company is going to be the first one there. Yeah, they're all still trying to get there. A lot of hype around it. You will find that in a lot of these there is actual metallic lithium inside them, so there's a bit of a concern there. The other thing is that sometimes these things are made under very, not only made, but used under very high pressure, because basically if those layers start separating, it no worky. So you have to keep a lot of pressure on them. To overcome that, some have decided to, well, why don't we take some of that nasty liquid electrolyte that we wanted to take out in the first place, and we'll squirt some of that back in there to fill in the holes, which works. But it's kind of 2 steps forward, 3 steps back. Now all of a sudden you've taken that somewhat, what was supposed to be safer, and went back to being less safe. There are a couple of other chemistries I had noted here, but we won't spend any time on the lithium sulfur sodium ion. Grab Wikipedia and read to your heart's content if you want to know more. That's my contact information. If you guys need anything, I'm a phone call away. If you want to call and talk to me for 5 or 10 minutes, glad to do it. If you want to call and talk to me for a few hours, that's called a consulting agreement. So, now, if anybody would like to come up and visit the lab sometime, give us a shout. We're happy to host you as long as we don't have things going on up there that you can't see. So, all right, that's it.
On behalf of the Atlanta Metro chapter, I'd like to thank you very much. And this gift on behalf.
Well, thank you so much, sir. I appreciate it.
Thanks again.
All right, you're welcome.
All right, folks.
We hope you enjoyed this presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.